Okay, let's get started. So far, you all have seen how can we use Newton's law of motion to describe the motion of a single particle. So, if I remind you what we have already done in the first handout, we started with the description of the motion of single particle. So we talk about the motion of a particle. And in this chapter, what we did, we started talking about how to describe the position of a particle. So we have position vector r. So r is the position vector, and this can be written using the x, y, z coordinates. And then we started talking about the instantaneous value, and the instantaneous value is given by the differentiation of that quantity. For example, if we want to get the instantaneous velocity, v is simply the differentiation of this position vector r. And when I write the instantaneous velocity in terms of dr by dt, it simply means you have to differentiate the x coordinate, differentiate the y coordinate, and differentiate the z coordinates separately like this. And when we talk about the acceleration is given by dv by dt, or this can be written as d2r by dt squared. It means that if we know the position vector, and if we want to get I mean the acceleration, you have to differentiate the position vector twice. So we have d2x by dt square, d2y by dt square, and d2z by dt squared. This is how can we use calculus to describe motion of the particle. Then in the second handout, we start talking about the effect of forces on a particle. And you should be familiar with these laws by now, the Newton's laws of motion. And in this chapter, we learned that force, or the net resultant force sigma F, is equal to the rate of change of momentum, where this momentum P is equal to m times v. So this is the momentum of a single particle. So you can think of this like we've got a particle of mass m moving with the velocity v. Its momentum is given by m times v. And I emphasize on the fact that the effect of force is to change the momentum of the particle, of the particle that we are interested in its motion. Then we make a transition from Newton's laws of motion, and we try to describe the motion of particle using the concept of work and energy. And in order to do this, we use the mathematical trick known as chain rule. We have to use chain rule. And what we did, we start with force equal to m dv by dt. So we consider a single particle is under the influence of a single force along one-dimensional motion along one axis, which is the x. And what we did, we use chain rule to change dv by dt to dv by dx times dx by dt. And this dx by dt is simply the velocity of the particle. So we have F equal to mv dv by dx, and then we are going to put the subscripted x on the F in order to denote that this force is along the x-axis. Then we are going to move the x to the other side like this, and then we are going to integrate it from the initial position to the final position, and we are going to integrate the velocity from the starting velocity to the final velocity. And then you see that on the left hand side we have the integration of fx dx, and this integration we call it work. Then the integration on the right hand side is simply 1/2 mv squared minus 1/2 mu squared, and this is the change in kinetic energy, and this is the change in kinetic energy. So we arrive at one of the very important principles in physics, and this is called work energy principle. Work energy principle or work energy theorem. So the work energy theorem states that the work done onto the system, equal to the change in energy. So the work done on the system equals to the change in energy. So this is what we call work energy principle. And when we look at this word energy, we've got so many kinds of energy in everyday life, starting from thermal energy, where we talk about heat, or we can have kinetic energy, which is the energy associated with the moving particle. We could even have the elastic potential energy, the energy stored in the object when we twist or change the shape of the object. For example, however, in this particular chapters or in this particular handout, we are going to focus on 3 types of mechanical energy. So we've got 3 mechanical energy. The first one is kinetic energy, Ke, and this is equal to 1/2 mv squared. We have gravitational potential energy, which is mgh, and we also have elastic potential energy, and this is 1/2 kx squared, and this is 1/2 kx squared. Then when we move on to the next chapter, we talk about the impulse momentum principle. Impulse momentum principle. And this principle is nothing more than just the restatement of Newton's law. So we start with the net force acting on a particle equal to the rate of change of its momentum. And what happened is we move dt to the other side. So we have sigma f dt equals to dp, and then we integrate on both sides, starting from the initial term to the final term. So this is the starting term that we consider the motion of the particle, and this is the ending term that we consider the motion of the particle. And on the right hand side we integrate momentum. So we start from the initial momentum P1. So this is the starting momentum of the motion of the particle, to P2, where we call this final momentum. And you see that on the left hand side we cannot do the integration because we don't know what force is it? So we are going to call this impulse. So impulse is the integration of f dt, and for the special case where this force is constant, you can bring this force outside the integral. So you would get sigma F, the net force, times T2 minus T1. So this is delta T. That's why sometimes you see people written or writing impulse equal to force times time. This equation is only true when force is constant, and because the impulse equals to the integration of f dt, it implies that if we've got the graph of f and t, the area under the graph of ft graph is going to be the impulse. It's going to be the impulse. However, if we look on the right hand side, the integration of dp, we can integrate this even though we don't know what force is it. So we are going to get p2 minus p1. So this is equal to the change in momentums. That's why the impulse momentum principle states that the impulse on the particle is equal to the change in momentum, is equal to the change in momentum. So this is basically the restatement of the definition of force. Impulse equal to the change in momentums. And then we are going to apply, we have already applied this impulse momentum principle in one of the case that is important in everyday life and especially in physics, and that is collision. When we consider the collision between two or more particles, so when these two particles, the particle number 1 and particle number 2 collide, this particle number 1 will push this particle number 2 with this force F2, and this particle number 2 will push this particle number 1 back in the opposite direction. And according to Newton's third law, this F1 is going to be equal to minus F2. It means that both forces have the same magnitudes, but they are in the opposite direction. And hence, if we look at 1 and 2 at the same time, if we look at both particles 1 and 2 at the same time, you see that the sum of these two forces, F1 plus F2, is equal to 0. So this implies that there is no net force acting on this system. The net force acting on the system is 0. And because the net force is 0, when we look at this impulse, which is force times time, because this force is 0, it implies that impulse is going to be 0. And when this impulse is 0, the change in momentum of the system must be 0 as well. So that's why we say that delta P of the system is going to be 0. And we have this conservation of momentum. What you need to be careful here is that if we consider just one particle like this, like for example, we are going to consider only particle 1, you'll see that if we consider this particle 1 is exerted by the force F1. So particle 1 is exerted by F1, and therefore there must be impulse on this particle, and hence the momentum of particle 1 will change. The momentum of this particle one must be changed according to impulse momentum principle. So the key idea is that if we look at both particles as a whole system, then the total momentum of a whole system does not change. However, if we look at uh, one particle, well, if we look at just one particle, like for example, we look at particle number one, then the momentum of just one particle will definitely change because there is a force exerted on it. So you must be careful about this point.